Okay, here's a Coke bottle, and we see the rays that we get as I move the beam from one side to the other. And we see how far the focus, or the point at which the beam hits the opposite side, moves. We see the beam moving back and forth about that far. Okay? And we could actually solve those triangles that we've seen and see just how much of the radius ought to correspond to this distance that the beam moves back and forth. Okay, so we see that the beam moves back and forth. It looks like about half the diameter of the bottle. Now here's a jar of honey. And let's look at what happens here. Okay, it looks to me like the beam is not moving back and forth nearly as much in relation to the diameter of the, or the radius of the jar. Maybe about that much, whereas if this was Coke, which is essentially just water, it would be about like that. And that indicates to me that the index of refraction of the honey is significantly higher than that of water. Again, I've estimated around 1.5, but I haven't been able to get set up to do a really precise measurement. Okay, so what happens, and this picture is really incorrectly drawn. This is the picture that's in your notes. I've got this refraction moving away from the normal, and really when we go from a higher index of refraction inside the cylinder or sphere to the lower index, we refract away from the normal, which means that the refracted ray really ought to be bent back toward the center. Okay, that's a nice straight line, isn't it? Okay, let's try to straighten it out a little bit. Okay, the refracted ray really ought to be more like this. So that's really incorrectly drawn, and you might want to make a note of that. The focal point, in any case, is what happens when we do this refraction here, and then we have this refraction here. Drawn right or not, the principle is still the same. There is a focal point, and we've observed that in experiments. The focal distance, well, it's a question for a thick lens like this where you measure the focal distance from. The focal distance would really be the distance from where we hit the where the rays first struck the sphere, not from here. But this distance here should be 2 minus n over 2n minus 2 times the radius. Now to get that, all we have to do is keep our angles straight and work out this refraction here. We first have to determine this distance, which is the distance that we just observed as the ray came through the medium to you. That gets a little bit complicated. You don't use anything more than simple high school geometry, but the number of angles and the labeling and so forth gets fairly complicated. I worked this out in my head on the way back from a conference, just as an exercise to keep me awake, to pass the time on a trip, and it took me about 200 miles to finally get it right. I don't remember how fast I was driving because I was concentrating on the problem. Fortunately, I don't think I ran into any police. Seriously, I was staying with the traffic. Trying not to get run off the road by tractor trailers and so forth, but mainly concentrating on this. And to get all the angles right and to remember everything from the first step to the last. Remember, I'm getting old here, and it took me a while. Had I written it down, I'd have probably written it down wrong the first 2 tries because I'm not real careful when I do that sort of stuff. But this is the correct relationship, and you might want to, as an exercise, try to work that out to see why it would be this. In any case, that's what it is. And using this relationship and finding focal points, we could measure the index of refraction of honey or any other material by simply measuring this distance and setting it equal to 2 minus n over 2n minus 2r. If we know the radius, which we can measure, then we can simply solve for n. Okay, here's a close-up of what I drew in class. I didn't draw this very well again. Theta r is going to be bigger than theta I, and it looks like it's almost the same. Really, this ray should be coming over about like this maybe, to show clearly that moving from the material with higher index of refraction to the material with the lower, we refract away from the normal. And here I've called the index of refraction n2. I wanted to say n equals 1 here. I couldn't say n equals n, so I had to say n equals n2. And there's the expression again for this distance.